So, now how many distributions are there when there are 3 levels, or how many distributions are there for a 3 level system? How many distributions? We saw that it is 3 distributions A, B and C, but can we get a number? Because we can get a number when we try to calculate indistinguishable particles in indistinguishable cells. Remember, we discussed about that before. Stars are like indistinguishable particles, and these are boxes, box number 1, box number 2 and box number 3. So, it is an indistinguishable particles in indistinguishable box problem. I think if you are not confused with now all this indistinguishability and distinguishability, then there are only 3 things that is possible. Particles are distinguishable, labels are distinguishable, that is one. Particles are indistinguishable, labels are distinguishable, that is another, and both are indistinguishable. So, we are talking about here both are indistinguishable. The reason is that since the labels are also indistinguishable, these 3 stars, it does not matter which box it belongs to, it will give you the same value. 2 star, 1 star, boxes are indistinguishable, does not matter, and of course, in this case anyway it has to be in all the 3 different boxes. So, this problem where we need to figure out that how many possible distributions are there when of course, there is no energy constraint or anything, it is a problem of partitioning an integer number. For example, if we have n particle which is partitioned into k labels, where both the particles and the labels are indistinguishable, it is equivalent to partition of n integer into exactly k groups, and that is denoted by p n k. For example, I will give you some example of that, and total number of partitions of course will be sum over k equal to 1 to n. Let me give you an example. If how many ways I can partition my 5? 5 is an integer, how many ways I can partition? So, okay, I have already an example, so I will just go with that. I will go with that. So, let us say I want to partition number 3. So, n equal to 3 here, and k can be 1, can be 2 and can be 3. Okay. In order to get that, how many ways I can separate my 3 into one part? Only one way, that is 3, because there is only one way. I am breaking 3 into only one way. How many ways? So, P 3 is nothing but 1. How many ways I can break 3 into 2 parts? 1 2 and 2 1 1 1 2 are the same. Okay, 2 1 and 1 2 are same, because they are indistinguishable indistinguishable boxes as well. So, 3 2 also can be only one way, and how many ways I can distribute 3 into 3 parts? Only one way, 1 1 and 1. So, you see P 3 then is sum of all that 1 plus 1 plus 1. So, it is only 3. Okay. So, as you can see that P 3 equal to 3. So, I am partitioning my 3 into 3 different possibilities, and it is denoted here. You see this distribution is nothing but P 3 into only one part 3 1. This is nothing but P 3 2, I am breaking into 2 parts, and this is nothing but P 3 3. So, first I will give example and then we will write. So, let us say I want to partition. So, we have seen that if I want to partition my 3 into different labels, I can do I can partition into only one group, which is 3. I can partition into 2 groups as 1 2, because 2 1s are equivalent, and I can partition into 3 groups as 1 1 and 1. Now, this one is typically called 3 in 1 P 3 1. This will be called P 3 2, because I am dividing 3 into 2 parts, and this will be called P 3 3, because I am dividing 3 into 3 parts. So, in general I am getting P 3 as the sum of all of that as 3. Okay. So, now let us do same for 5. Now, 5 can be divided into one group as just one way 5. 5 can be divided into two groups as 4 1 or 3 2. 1 4 is same, 2 3 is same, and is there any other way? No. So, 5 can be divided into two groups as only these two possible ways. 5 can be divided into three groups as 1 1 1 1 2 plus 3 1 1 3 one way, 1 2 2 other way. Is there any other way I can divide it? No. So, that is a possibility. Now, 5 can be divided into 4 groups as 1 1 1 2 and no other way, and 5 can be divided into 5 groups as only one way 1 1 1 1 1. So, now those, which means that I can write P 5 as sum of phi 1 plus phi 2 plus phi 3 plus phi 4 plus phi 5. Now, phi 1 I got as 1, phi 2 I got as 2, phi 3 I got as 2, phi 4 as I got 1, and phi 5 I got as 1. So, 2 plus 1 3 5 6 7. So, P 5, that means 5 integer can be partitioned into all possible ways in the 7 possible ways max, which is then equivalently saying is that 5 particles can give rise to 7 possible distributions if I do not constrain my energy. If there is no energy constraints there, then I can get 7 possible distributions. So, just like from 3 we got 3 distributions, from 5 I can get 7 distributions. Now, how do I know for a general number? Do I have to write like this, or is there any better formula available? So, let us see that. So, skip this part. So, this part I have just shown you this just now. So, as I said that for 5 it will be 7. Now, what is the general formula? So, the general formula for large n is very complicated. We are going to show you in Mathematica just now. General formula is very large, it is exponentially it will increase, but there is a recurrence relation that one can use, and that is P n comma k is P n minus 1 comma k minus 1 plus P n minus k comma k. This is a recurrence relation, one can use that. By the way, this part is outside the syllabus, this is if you are curious only, then only you can look at it, otherwise the best way to do is just to look and see how you can partition that, and we will not use in the exam a much higher number of n or k, but this is just for the curiosity for curious students. If you want to understand how it can be done, this is a subject called partitions in number theory, and using this recurrence relation we can get that. For example, if I take an arbitrary n and k, I want to try out 11 particles into 3, how many possible ways I can do that. So, if I want to do that, I have to do the same formula n minus 1 k minus 1, which will give me 10 2 plus P 8 3. Now, 10 2 can give me 9 1 plus 8 2 n minus k k plus I have 8 3. Now, 9 1 or anything 1 k, when k equal to 1, there is only one way of doing it. So, I have to divide my integer into one possible ways, that will give me always 1. Now, 8 2 can be again 7 1 plus 6 2, and 8 3 can be 7 2 plus 5 3. So, 1 plus 7 1 can give me only one way, whenever there is k equal to 1, there is only one way. 6 2 I can write as 5 1 plus 4 2 plus 7 2 can be written as 6 1 plus 5 2 plus P 5 3 is already there. So, P 6 1 can be written in also one way. So, I have got 3 already plus this one also can be written in one way, 3 plus 1 4, 4 2 can be written as 3 1 plus 2 2. Now, 5 2 can be written as 4 1 plus 3 2, and 5 3 can be written as 4 2 plus 2 3. Now, that will be interesting. Now, you see 3 1 is also 1, 2 2, that means integer 2 dividing into 2 parts, that is only one way. So, this also gives me 1, 4 1 also will give me 1, 3 2 dividing 3 into 2 parts, only one possible way, 1 and 2, 3 into 2 parts, that is only one possible way, that also will give me 1. So, now I have 3 plus 1 4 plus 1 5 plus 1 6 7 8 9, I got already 9 there, plus I have to still break P 4 2 and P 2 3. Now, whenever n becomes less than k, 2 less than 3, that means how can I divide 2 into 3 groups? Minimum I may need 1. So, this is going to be 0. Now, what is 4 2? 4 2 is, again I can do 3 1 plus 2 2. Now, you know 3 1 is also 1 and 2 2 is 1. So, I am getting 11, 9 plus 3 1 is 10 plus 2 2 is 11. So, I am getting 11 as the number. You can verify this. So, we got P 11 3 as 11, and we can verify that with Mathematica. I will just do one more time just to check. So, P 11 3 is P 10 2 plus P 8 3 equal to P 9 1 plus P 8 2 plus P 8 3 equal to 1 plus P 7 1 plus P 6 2 plus P 8 3 is 7 2 plus P 5 3 equal to 1 plus 1 2 plus P 5 1 plus P 4 2 plus P 6 1 plus P 5 2 plus P 4 2 plus P 2 3. 2 3 is going to give me 0, 5 1 is going to give me 1. So, 3 plus P 4 2 can be 3 1 plus 2 2, 6 1 is giving me 1, 5 2 can be 4 1 plus P 3 2, 4 2 can be 3 1 plus P 2 2. So, now 3 1 is giving me 1, 2 2 is going to give me 1, I have already 1 available here, 4 1 is going to give me 1, 3 1 is going to give me 1, and 3 2 also is going to give me 1, and 2 2 also is going to give me 1. So, I do not have to do any more. So, this is 3 plus 1 4 plus 1 5 plus 1 6 7 8 9 and 10. So, I am going to get 10. So, P 11 divided into 3 is giving me 10. 10 possible ways I can do that, as you can see. So, it is 10, P 11 3. So, how did I do that? So, actually I said P 11 3 means maximum up to 3. In fact, we no, P 11 3 is like all only 3 possible divisions, which in Mathematica, as I can I show, is that there are like few possibilities I will write. One is that 9 1 1 is one possible ways to break it, 8 2 1 is another possible way, 7 3 1 is another possible way, 6 4 1 is another possible way, 5 5 1 is another possible way, and 4 6 1 will repeat as 6 4 1. So, we will not do that. Now, 1 we have to change. Now, I can say 8 1 2 is one possible way, 7 2 2 is another possible way, 6 3 2 is another possible way, 5, 4, 2 is another possible way, is it 5, 4, 2. Now, 4, 5, 2 will repeat. So, now instead of 2 we are going to go to 3. So, if we will start with 7, 1, 3, 6, 2, 3, 5, 3, 3, 4, 4, 3. Okay. Now, I am going to go to 4, which is going to match. Now, let us see how many are there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. 821 and 812 are same, and then any other same. 731 and 713 will cancel out. 623 and great. So, that gives me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, these are the 10 possible ways that 11 can be broken into bunch of 3. So, you can say that I am going to get from 11 particle and 3 labels in which all the labels have same energy, I can get this many possibilities, and each of them however will give rise to a number of microstates. And without doing much calculations, I can say that this will give us the most probable distribution, because or we have to check it is like should be close. So, 11 divided into 443 will be the equal possible divisions. Actually, ideally 444 is the, if for 12 particle will be the equal division, but it is closest to the equal division possible into 3 groups. So, that this one will give us the most probable distribution. So, now we see that how we can get distributions. Now, with the number of particles, the number of partitions will increase exponentially, as you can see with this formula, which is only true by the way for only large number and not for the small number. So, you can not use that for n equal to 11 or 12, you have to use like huge number to show that. So, I will show here the plot of number of partitions like P n as a function of n. So, I will just clear it out for you to check the figure, and you can see that when the number goes to 100, this P n goes to more than 10 to the power 8, as you can see, goes to more than 10. So, number of partitions becomes huge, just for you to see that how the number of microstates actually is going to change with the number of particles, enormous. So, now coming back that to the fact that we talked about indistinguishable particles and indistinguishable boxes. Now, we are going to talk about indistinguishable particles and distinguishable boxes, and the reason is that we are going to put energy into particles, and we know that energies are indistinguishable. So, this problem is typically called star bar problem. So, here how many, the question is that how many ways I can distribute 5 quanta of energy into 4 distinguishable particles. Now, 5 quanta of energy is denoted by 5 stars. Stars are indistinguishable, energy is indistinguishable. So, just a different way you have to think. So, earlier we were talking about indistinguishable particles in distinguishable boxes with these examples, right. This is indistinguishable particles and these are distinguishable boxes. I was saying describing this way, right, but now the boxes will be distinguishable based on the bars. So, whenever I put 2 bar, I essentially have 3 boxes, and we can call those boxes as 1, 2 and 3. Now, if I have in box number 1 2 units of energy, I will put 2 stars. If I have 3 units of energy in box number 2, I will put 3 stars here. So, like that I will divide 5 stars into 4 boxes. Now, you know that for 4 boxes how many bars we need? We need 3 bars for 4 boxes, right. See 1, 2, 3 and 4, I get 4. With 3 bars I can make 4 boxes. So, that means now I have all total 1, 2, 3, 4, 5, 6, 7 and 8 things, which is number of stars, which I can call it as R, plus number of boxes minus 1, because that is going to give me the number of elements now. Now, you see in these elements, so that is the number of spaces that I have 1, 2, 3, 4, 5, 6, 7 and 8. I have 8 spaces. Why? Because my number of stars is 5, number of distinguishable particles is 4 and minus 1, that gives me 8. So, you can see that why I am getting n minus 1, because n minus 1 bar will give me n boxes, and that is the reason I am getting n minus 1. Stars are just 5, so I kept as 5. Now, what I am saying is that I have now 8 spaces left, and in 8 spaces I can put my these 3 bars in whichever way I want to. I can put them consecutively 3, I can put them all at the same time, then all my stars will be here. That means, in one box only the stars are there, other box are empty, or I can put all the stars on the first box itself. So, if there is no I will just explain it a little bit here. So, let us say I have let us say 2 star and 1 bar. 1 bar essentially means there are 2 boxes. So, I have now these 3 items, star, star and a bar. So, I have basically 3 spaces. I can put my bar wherever I want to. Let us say I put my bar here, my star here. That means, one box is empty, this box number 1 is empty, and box number 2 is having 2 particles or 2 particles or 2 units of energy. Similarly, I can put my bar here, then each box will have some units of energy, or you can say that if stars are units of energy, then particle number 1 has 1 unit, particle number 2 has another unit of energy. Okay. And let us say if I put my bar here, then this particle number 1 will have 2 units of energy, or particle number 2 will have 0 units of energy. So, you see that in 3 spaces, wherever I put my bar, accordingly that will work. So, now the thing is that I have therefore r number of stars plus n minus 1 number of bars. This many spaces I have, in which n minus 1 number of bars I can put wherever I want to, and that will distinguish the particles or energy levels into different distinguishable particles. You can say indistinguishable particles into different boxes, whichever way you can think of. So, imagine that you have 3 particle or 3 units of energy and 2 boxes. So, 3 units of energy is R equal to 3, 2 boxes is n equal to 2. Now, 2 box can be obtained by 1 bar. Left hand side of the bar will be a box and right hand side of the bar will be another box. Let us say call it box number 1 and box number 2, or we should stick to, according to the problem, that a bar will give us 2 particles, particle 1 and particle 2, and the stars are energy levels. So, I have 3 units of energy and I have 2 particles. Okay. So, now what I am going to do is that essentially I have 4 elements now, 1, 2, 3 and 4 elements. Now, just imagine them as elements. I have these 4 elements. These 4 elements, out of these 4 elements, I can put this bar in any of the 4 places. So, since I have 4 elements, I have to keep all those 4 elements, let us say, somewhere. So, these 4 elements can be put into these 4 places. Now, how many ways I can put my bar? I can put my bar in any of the 4 places. I have 4 things and I have to choose one out of that. So, I can do it in 4C, 1 ways. How many ways I can choose my bar? That is fine, right? How many ways I can choose my bar? Meaning whenever you choose something, you basically decide where you are going to place, because there are 4 things. You have to keep all the 4 things on the floor, right? Now you can put your, let us say you have a bar and 3 stars. You can put the bar front and 3 stars, or you can put the bar second place or third place. Correct. So the depending on the position of the bar, the stars will be divided. Earlier, like box are fixed, because star or bar are imaginary things. Stars are nothing but units of energy. If one box has 2 star, means that particle has 2 units of energy. If another box has 3 stars, that particle has 3 units of energy. So particles are distinguished by the boxes, and stars are just units of energy. So in general, I have r plus n minus 1 number of items, star bar included, from which I choose n minus 1 bar, and that is the statistics W for indistinguishable particles in distinguishable boxes or indistinguishable energies in distinguishable particles, whichever way you want to think. Okay. Now let us go back and see that is it working or not. So this is the formula that I showed, r plus n minus 1, r plus n minus 1, C n minus 1, and that is this formula. Now imagine this problem of 3 particle and 3 boxes. So 3 particle and 3 boxes is 3 units of energy and 3 particles, sorry, 3 units of energy means r equal to 3 and 3 particles means n equal to 3. So number of ways is 3 plus 3 minus 1, choose 3 minus 1, which is 5C2. And what is 5C2? 5 into 4 by 2 into 1 is giving me 10, and 10 was the total number of possibilities obtained when 3 units of energy were distributed in 3 particles. Remember that, right? So if I distribute 5 units of energy, if I use 5 units of energy, so r equal to 5 into 4 particles, that means n equal to 4, how many we will get? 5 plus 4 minus 1, C 4 minus 1, which is 8 C 3, which is 8 into 7 into 6 by 3 into 2 into 1, 3 and 2 6, 56. So we will get 56 total number of possibilities of distributing 5 units of energies into 4 particles. Is that clear? Okay. So which situation I am doing that? Where my particles are indistinguishable and boxes are distinguishable. I am doing that, or I can think of as a distributing some units of energy into distinguishable particles. Same thing I am saying, one is indistinguishable, another is distinguishable. Not both are distinguishable, not both are indistinguishable either. If both are indistinguishable, we go to partitions. If both are distinguishable, we either go to n to the power r, or we go to the permutation combination thing, or we go to the n factorial by n1 factorial, n2 factorial and all that. This is where we talk about indistinguishable particles and distinguishable boxes, but in our problem we will be mainly concerned with indistinguishable energy units to distinguishable particles, because classical particles, as I said, are distinguishable, and with there we are putting the energies. You will see later on indistinguishable particles, distinguishable boxes or energy levels will be important for boson and fermions quantum statistics, because boson and fermions are all indistinguishable, but the boxes where you put it, they are distinguishable. So boson and fermions, these statistics will become important, whereas the other one where he said that all particles are distinguishable, boxes are distinguishable, in that case the Maxwell-Boltzmann statistics are important. Okay. So here we are getting a handle of that total number of possibilities how one can get. I will just clear this marking, and then 56 we got it here, as you can see, 10 we got it here, as you can see, and these are the 10 values. Remember, here particles are indistinguishable, the stars, Here I am talking about not energy units, I am talking about actual particle, actual ball, or you can think of that as energy units, whichever way. And the boxes are distinguishable 1, 2 and 3, or you can think of them as particle. So, let us say this is particle number 1, this is particle number 2, this is particle number 3, and the stars are energy units, and you see these are the 10 possible ways that you can arrange. These are all total 10 possibilities, in which however, we have 3 different distributions, and each distribution has different possibilities like A, B and C. So, A has 3 possibilities, B has 6 possibilities, and C had only 1 possibility. So, this gives me this formula n plus r minus 1 C n minus 1 gives me the all total possibilities, all possible distributions they gave me. They do not give me just one distribution, they gave me all possible distributions. So, if I have 9 units of energy and 7 particle, how many we should get? 9 units of energy, 7 particles. So, 9 plus 7 minus 1 C 7 minus 1, which is 15 C 6, and you know what 15 C 6 is. But if I do the opposite, 7 units of energy into 9 particle, how many we get? Now, it is 7 units of energy, it is 7 plus 9 minus 1, choose 9 minus 1. So, it will be 15 C 8, not 15 C 6 anymore, and that will give you 6 4 3 5. You are not getting the same thing, because one is indistinguishable, another is distinguishable. That is why you are not getting the same thing. You see, in one case 9 units of energy and 7 particle, in another case 7 units of energy and 9 particle. Now, energy units are indistinguishable, particles are distinguishable, that is why you are ending up with 2 different statistics. Okay. So, now this fact that r equal to 5, that means 5 units of energy into 4 possibilities giving us 56. How do we get that 56? That we are going to talk about now. Multiple levels and constraint distribution. Why do I say constraint distributions? Because my number of particle is fixed and my energy is also fixed. My energy is what? 5 unit, and what is my number of particle? 4 particle. They are all, both are fixed. How can I do that? I can do that by drawing the labels, simple labels, and distributing them. For example, my units of energy is 5. So, I put 1 particle in 5 and I put 3 particle here. So, I have 4 particle, right. This is one possible distribution. I can now have another possible distribution as this one. I can have another possible distribution. So, now it is 4 and 1, now it is 3 and 2, now it is 3 and 1 1, now it is 2 and 1 1 1, and now it is 2 and 1 and 0, 2 2 2 2 1, and each of them has now different W's. So, now I got 6 possible distributions A B C D E F. I do not know whether you can get any more, you can check that. 6 possible distributions. Now, how do I get the W equal to 4? It is, there are 4 particles. So, factorial 4 divided by factorial 3, there are 3 particles in one box, right. Factorial 3, factorial 1, and all are zeros. That will give you the 4. How do you get 12 here? You have to do again the same thing, factorial 4 by factorial 1, and factorial 2. This will give you 4 factorial is how much? 24. 24 by 2 is 12. So, you will get 12 here. This is the same as this formula, this is same as this formula, the same as this formula, this is 3 1 distribution is same as this formula, and this is same as the first formula. So, as you see, the total number when you add them up is 12 plus 12 in there are how many 12s? 12, 12, 12, 12, 4 12s. So, 48, 48 plus 4 is 52, 52 plus 4 is 56. So, there are total 56 possibilities, which we already got from r plus n minus 1 C n minus 1, we already got 56, right, and this is how the 56 is breaking into 6 possible distributions. And then what is the most probable distribution? There is not one that is single most probable distribution, all B, C, D are and F are all most probable distributions, because we really cannot they are all equal, and that is, this situation is coming because of this smaller number of particles, smaller units of energy. It is basically will not come when there are a huge number of variations are there, but this will give you an idea that how one can distribute energies into particles.